So if it doesn't work, I'll reclaim. Oh, no, it looks like it's working. I've got a little cloud with a red button on it.
Okay.
Good.
Yeah. Hopefully it's going to the correct cloud.
Hope it's going to the right space, right?
Otherwise, I don't know where that's going.
We'll find it eventually. Okay. Should we start?
Yeah, I think we're good. We can start.
Well, hello, everyone. Welcome to the monthly webinar of the IRSIG. My name is Lisa Locke, and I, with Meredith's help, will be moderating the webinar today. I'm an engineer. I work at the National Radio Astronomy Observatory, and I'm a member of the IRSIG Leadership Council. Now, before I introduce our speaker, I'll provide some brief instructions on how the webinar will work. These are exactly the same instructions that are in the chat window, so you can scroll up and read them or listen. One is please submit, actually, the questions we decided what we should do is just, Zoom has the option of raising your hand. So if you if you have a question, you can either, I guess, type it into the chat window or raise your hand, and we'll watch for you and see if we can insert you into the right part of the talk. But then if your question isn't answered at the end of the talk, we'll have a Q&A period, and we'll either let you speak or just verbally read your question. So number two, please submit any feedback, comments, questions for the Leadership Council through the chat window as well, and we can answer these questions at the end of the hour. You can also send us an email response afterwards if we run out of time. Please report any technical difficulties if you have trouble hearing anybody, seeing in the chat window, so we can address them. And this webinar will be recorded and available to be viewed later on our webpage. So now I'll introduce the speaker. We're very pleased to have our speaker today. Her name is Dr. Maria Drozdovskaya. She is currently a Swiss National Science Foundation Ambizioni Fellow at the Center for Space and Habitability at the University of Bern in Switzerland. Her research covers the topics of astrochemistry, star and planet formation, and comets. The overarching goal is the search for our astrochemical ancestral tree. She defended her PhD thesis on October 2016 at the University of Leiden in the Netherlands, supported by the Huygens Fellowship. And subsequently, she began working at the University of Bern as a CSH and IAU Gruber Foundation Fellow. She is a co-chair of the International Astronomical Union Working Group of junior members. And today she will be speaking about ingredients for solar-like systems and perspective in infrared. So without further ado, this is Maria.
All right, good evening. Probably I'm the only one in the evening zone. So good afternoon to the majority and good morning, just in case you're on the morning time zone. So Lisa, Meredith, thank you very much for having me. It's my pleasure to give my first webinar ever. So if something is wrong from the technological point of view, please do let me know in the chat, and then hopefully I can fix it. So as was just announced, I will tell you today about the ingredients for solar-like systems and what we can do on this topic in the infrared domain. So without further ado, let me begin by telling you how to make our solar system. So as you all, or at least the majority of you, still have to have dinner, I will give you a recipe how to make soup, actually. And I will tell you how making soup is actually the same as making our solar system. So when you want to cook soup, what you want to do is, first of all, prepare all your raw ingredients. So you take out all the vegetables that you will need out of your fridge, put them out on the kitchen counter. And this is essentially what happens in the prestellar stage of star formation. When you are in the prestellar phase, you set out all your initial small dust grains, all your atoms and all your molecules. And at this stage, no star formation occurs yet, and you're just getting ready to make things. Now, thereafter, you're going to chop up your vegetables, and then this is essentially the onset of star formation. At this point, you're going to initiate gravitational collapse. You're going to form a central protostar with a protoplanetary disk around it. And initially, this will be the so-called embedded phase of star formation. So you still have an envelope around this young system. At the same time, you also have bipolar outflows near your protoplanetary disk, which will start cleaning out the surrounding envelope material. And so this is really your bulk cooking process. Now, suppose thereafter you want to add some meatballs to your soup. So you have to assemble these meatballs. And so this is actually something that happens with the protoplanetary disk when you're converting your little dust grains into bigger objects, say kilometer-sized comet bodies, and eventually several thousand kilometer-sized planets. And in the end, once you're done with all of that, you're going to have your prepared soup that you're ready to eat. And in the case of the solar system, you have the mature solar system that we have today. Now, what happens when we go to a restaurant and we get a gorgeous dish in front of us? We don't actually know how this dish came to be. And this is actually something of a situation that we find ourselves in right now when we have our mature solar system, but we don't quite know what it was originally made from and what the cooking process was. So there are a few ways we can try to trace back in history and figure out how our solar system was made. So one thing we can do is we can sneak into the kitchen of the restaurant and look at the leftover mess on the kitchen counter. And so for us, this means looking at things like meteorites, asteroids, Trojans, centaurs, and comets, essentially all these leftover building blocks from the cooking process of our solar system. And then, of course, if, for example, somebody else is still busy cooking the same thing in the kitchen, then you can actually see and figure out what they're doing. And so by this analogy, what we can do is look at other low mass systems, such as those comparable to our young sun, and see how they're being formed. So for this case, I will focus in my talk a lot about the low mass binary system IRIS 16293. So this name will come back later in the talk, and this will be the solar-like neighbor that we will assume is evolving analogously to our solar system earlier in the day. So also in this talk, I will predominantly focus on volatiles. And when I say volatiles, I mean the gas and the ice. And I will not so much focus on the refractories, so the dust and the rocky component. So as I mentioned, one way to figure out the history of our solar system is to look at the leftover building blocks. And comets are believed to be some of the most pristine leftovers of the innate protosolar disk. And this essentially comes from the dynamics analysis, as comets spend most of their time far away from the sun, and so are typically are very cold and at very large disks from our sun, and so should be the most pristine leftovers that we have. We also know that they have large reservoirs of volatiles because they have these large gaseous coma, which then help us observe these bodies in the sky. And in fact, we already have a very long history of ground-based observations that have shown us that there's a large variety of volatile molecules on comets. And most recently, the ESA Rosetta mission has uncovered a very big variety of molecules on comet 67P in particular, and will be a central focus point in my talk as well. So the Rosetta mission was very special in the sense that we were able to spend something like 2 years at comet 67P orbiting and even making a landing. And so being able to really monitor what happens to a comet as it's approaching the sun and experiencing perihelion. For the case of the volatiles, I think the main finding is that we have this huge zoo of molecules, as has been summarized, which contains everything from long carbon chains to very probiotically significant species like glycine, noble gases, and even more work that is still ongoing. So rather than trying to figure out exactly how every single one of these came from, I think the main takeaway from at least these findings is that comet 67P and the Rosetta mission are essentially telling us that the raw ingredients for our solar system were very chemically diverse and complex already at the time of its formation. So as I mentioned before, it's typically assumed that comets are some of the most pristine tracers of our solar system's past, but we do have some pieces of evidence to back this up as well. So for example, as was revealed by the CONSORT and RSI instruments on the ESA Rosetta mission, it seems that the nucleus of Comet 67P is homogeneous. Observations with the MERO instrument and also supportive models have shown that a perihelion passage of this comet at 1.2 AU from the sun will only in fact heat the outer 10 centimeters of the comet, which means the interior of the comet will still remain pristine. It has also been determined that there is a very high D2O over HDO ratio relative to HDO over D2O. So the ratio turns out to be 17 rather than the statistically expected value of 0.25. And so again, deuterium is a typical signature for a cold formation and a cold long-term past. And then finally, some of the species that have been found are CO and 2 and noble gases, which are in fact highly volatile, and they've also been shown to be very abundant in 67P. So again, all pointing to a cold, unprocessed interior of Comet 67P. So if we want to now figure out what the solar system was made of, and now we assume that 67P is a representative pristine tracer, then we also want to actually figure out what the bulk abundances are. And cometary studies have shown that there is a large variety day to night, also seasonal varieties. And so in fact, many of the earlier observations may just be a mere snapshot of what the cometary molecular inventory is like. So essentially only with the Rosetta mission do we have this unique chance to try to figure out what the bulk abundances may be, because we were at the comet for so long and were able to monitor the changes and the evolution. And so there seems to be this preferential period at the end of May towards the very early beginning of June in 2015, which is very suitable for the derivation of the actual cometary bulk abundances. So this time period essentially corresponds to when the comet was sufficiently close to the sun to thermally desorb water, which is the dominant volatile in the comet, but also sufficiently far from the sun to prevent very significant dust pollution. Because when the comet was at perihelion, there was so much dust in the coma that in fact the Rosetta mission could not be very close to the surface and do very accurate measurements of the least abundant molecules, simply because it was too dangerous for the spacecraft. So this May to June period is optimal for these reasons, and this is the basis of the bulk derived abundances that I will present to you hereafter. And also as a note, this May 2015 period corresponds to the summer of the Southern Hemisphere. As an additional argument, this hemisphere is thought to be less covered by resettled dust from previous perihelia. And so again, is an argument for the most pristine, most appropriate sample of the data. So suppose now that we have uncovered something about the chemical composition of our young solar system, now let's go look over at our solar-like neighbor and figure out what this neighbor is doing, and to see whether the chemistry that we're going to make the solar system from is comparable or whether it's different. And so, as I mentioned earlier, the selected source for this is IRS 16293-2422, which is a binary source, so it has source A and source B. So if all is well, you see my mouse. So here's our source B that you can see in the 0.87 millimeter continuum. The source is relatively close to us, 141 parsec away, and source B is roughly 0.1 solar mass, and it's still in the earliest embedded phase of star formation. So around this binary source, there's still a huge envelope on the scales of several thousand AU that is covering it up. So around source B, which is the one that we're going to focus on as our referential solar-like analog, observations have shown that there is a disk forming, which is roughly 50 AU in size. So a protoplanetary disk that is comparable in size to our solar system. This is stemming from dust and gas observations. And so for all these reasons, being low mass, having a disk on the same type of size as the solar system, this is essentially our key arguments for considering it essentially a younger solar system in the making. Now, you may ask why choose source B rather than A, and the reasons for this are essentially observational. So it seems that source B has a disk that is more preferentially positioned in the sky. It's face on, and so the velocity gradients that we see are easier to interpret. So you have very nice narrow spectral lines when you're observing source B, so making them easier to analyze and to uniquely identify, because if you have a very large velocity, then you're going to Doppler broaden all your spectral lines, and then you're going to suffer from line blending. In regards to the relative age of the two sources, this is something that seems to be somewhat inconclusive for the moment. We don't know whether source A was born first or whether A and B were born at the same time, but there's still definitely signatures of infall towards the binary system. So it is really young. So we had a great opportunity to observe the source with ALMA, namely with the so-called PILS survey, the Protostellar Interferometric Line Survey, which was an extensive ALMA observational campaign led by Jes Jorgensen. And we were able to observe a huge spectral bandwidth in band 7 and identify many of the spectral lines. There's still some unidentified lines remaining, but out of the ones that we were identified, we were able to find roughly more than 100 different types of molecules. So it seems that this IRIS 16293b, it's very chemically diverse and complex already in this early embedded phase of star formation. And so what you see on the figure is showcasing essentially the abundances that we can now probe this source. So you see the dashed line, which corresponds to the methanol abundance. So we're now probing 5 orders of magnitude in range of the different species that we can see there. And so this is really the showcasing the power of ALMA as well, because it has not only the spatial capabilities to really zoom in on these young systems and on the disk scales in them, but is also showcasing its sensitivity where we can find the least abundant molecules with the weakest lines. So the story that I would like to tell you is goes essentially around combining the data from this ALMA survey, so the PILS survey, and from the Rosetta mission, specifically from the Rosina instrument. So as I've mentioned, ALMA was great for studying the source, high spatial resolution, so we're able to get down to the disk scales and really probe this 50 AU range where we're thinking that we have this protoplanetary disk. We have great spectral resolution. We can spectrally resolve our narrow lines there. And because we had this large spectral coverage, it's really one of the most complete spectral characterizations of a low mass protostar on essentially the same spatial scales. Whilst before we had great facilities, but we could only do little chunks at a time in different spectral ranges at different spatial resolutions. But now we have this really consistent data set. Now, the reason to combine this with the Rosina data specifically from the Rosetta mission is because it was, again, one of these amazing data sets that allowed us to probe a full chemical inventory in a very consistent fashion. So allowing us to derive these bulk abundances and also combining it, the power of this instrument in particular with its very high mass resolution. So for example, there was the ability to finally separate CO and N2, which is very difficult if you do not have a sufficiently powerful mass spectrometer. And another plus of the Rosina instrument is that it also had a very wide mass range. So you could get the simplest volatiles, but at the same time, you could also get the larger, heaviest molecules in essentially one consistent measurement. So observations of interstellar objects and comets have been combined before. So this is something that has been done by Dominique Bouclet-Morvan for the case of the comet Hale-Bopp, and at the time, the best available collection of interstellar sources. And so the exercise that Dominique had performed was to try to group molecules by their chemical families. And when she looked at CHO-bearing molecules, what she saw is that there was essentially correlation if you look at the abundances of these molecules relative to methanol as you saw them in the comet, so what you see on the x-axis, and then these molecules again relative to methanol if you were to look in the ISM sources, so then this is your y-axis. So now if I repeat this exercise with the more powerful ALMA observations towards a single source on disk scales, and now our more well-defined the bulk abundances for Comet 67P from Rosina, we're recovering this strong correlation in the CHO-bearing molecules, which has been seen before. For the nitrogen bearings, for the case of Hale-Bopp, there was also a correlation seen earlier by Dominique. And if we perform this exercise now for 67P and IRIS 1693B, then again, we're recovering this correlation. Now, for the case of sulfur-bearing species, the situation is more troublesome. It was more troublesome before, so it was not so clear whether there was some sort of correlation between the ISM sources and the comet. Right now, the case is somewhat stronger for the correlation between the two sets, although a large spread does remain. So there's, for example, CS has a very large error bar, and this has to do with the Rosina measurements because it's hard to distinguish it from overlaps in the mass. And then also SO and SO2 are tricky from the protostellar point of view because they're also very strong outflow tracers. And then the Rosina and the ALMA data also allowed us to, for the first time, probe something new. So there's an attempt to probe phosphorus and fluorine bearing molecules and see whether the correlation extends to them as well. And actually, in fact, we have upcoming ALMA observations dedicated to phosphorus bearing PO and PN to verify these numbers and make them more robust. So to summarize all of this into a single plot is essentially done in this figure here, where the color-coded are the different families, so CHO, N, S, P, and CL, and then relative to their specific reference species. And what you see is that the data points roughly fall on this 1-to-1 line, or at least a factor of 10 to either side of it. So I think what this is telling us is that all these chemical families, they're correlating between the protostellar environment and what we have in our comet. Yes, we have some scatter, which is probably natural, but there's definitely some correlation in here. So this probably implies that there is, to some extent, a preservation of material between the earlier phases of star formation all the way into a cometary body, which preserves the material that was in the earlier protoplanetary disk. So if you did pay closer attention, then you would also see that predominantly the cometary relative abundances are somewhat higher preferentially than the protostellar ones for the case of the CHO and the N-bearing species. So a lot of the pink and the blue dots, they predominantly lie to the right side of this dashed line. So this implies that perhaps there's some destruction of volatile molecules near the protostar before this material enters the protoplanetary disk and then subsequently into the comet. Or perhaps some additional material was produced somewhere in the disk before it was incorporated into the comet. And of course, the final possibility is that it could be something to do simply with the reference molecule that you take, which is methanol, or its nitrogen or sulfur-bearing analog. For the case of this plot, this is essentially these three scenarios I cannot exclude based on this data alone. So all in all, the conclusion is yes, there's some preservation, but some alteration does occur. So you may argue also that at the moment we're making big conclusions based on one comet and one protostar, but we do have some evidence to suggest that both of these are not atypical if you consider the larger set of these bodies for the other ones for which we don't have equally great data. But for example, this bilobate shape of comet 67P is something that has been seen before for Hartley 2 and also for this trans-Neptunian object, Mu69. The heterogeneous surface is also similar to the surface that was seen for comet Wild 2. The dominant volatile for 67P is water, and which is hidden in its interior and is absent from the surface. And this is something very typical of almost all comets. The low density, high porosity of the nucleus are comparable to comet Tempel 1. It was somewhat of a fainter comet in comparison to other ones, but not abnormally faint either. You may think that perhaps this chemical richness that the Rosetta mission uncovered is something only unique to 67P, but this is likely a consequence of the superior measurement techniques that we had because we had this long-term monitoring, because we were able to approach so close to the surface and perform these high sensitivity measurements. And for example, complex molecules like ethylene glycol and formamide and others now are being detected with remote sensing techniques on other comets as well. The volatile composition overall also does not seem to have great differences from other comets. And then finally, also for the case of IRIS 16293b, this binarity that we see for this source is very common. Multiplicity in general is normal in star forming regions, even in low mass star forming regions. You may think that perhaps this crazy chemistry that we're seeing towards the source is also special and may be something to do with just the source. But again, all these molecules that we're seeing have been found before for high mass protostars and are now being more and more routinely detected towards low mass sources. And so, for example, in comparison to L483, it compares very well. Again, probably all the different molecules that we're able to detect here are just the lucky set that we were able to obtain with ALMA. The physical structure for the source is, again, nothing out of the ordinary, and this bridge structure that you see between the two sources has now also been predicted by simulations of binary information. So in this regard, I think what we have is a typical solar-like system in the earlier phases of formation and a representative cometary body. And so based on these arguments, I think these results should hold even once we push forward in our efforts and extend our samples, because of course we want to check that this is indeed true. So the question that you may have is, why not compare with protoplanetary disk gases directly? Because I've been telling you about this embedded protostar, and sure, we're getting down to 50 AU scales, but we're not sure that we're observing the protoplanetary disk gases. we do not have the velocity signatures because it's an embedded source, and so we cannot detect the disk as easily if it's already a mature enough protoplanetary disk with Keplerian rotation. But essentially, there's a more practical and observational reason for not being able to do the comparison directly with a protoplanetary disk. So ALMA has been great in allowing us to resolve disks, but it has also, of course, brought its complications, and it has revealed to us that the structure of disks is very far from trivial. So there seems to be a lot of radial structure on smallest scales around the protostars. So there are these rings, even in the molecules, not only in the dust, but also in the molecular tracers. And in fact, what we want to compare to if we observe a disk is midplane, so the most inner, densest parts of a protoplanetary disk. And those are very hard to observe. So in order to actually probe the midplane of a protoplanetary disk, you have to go down to an abundant molecule such as CO, but then to one of its rarest isotopologues, ideally a double isotopologue, to then be able to probe the optically thin emission coming from the deepest layers. And otherwise, you cannot observe directly to the midplane because you will be blocked by optically thick problem. And then finally, this huge inventory of molecules, and including many complex organic molecules, is not currently feasible for protoplanetary disks. And in fact, we don't know if this is something that we're currently limited by the observational facilities, or simply from the physical chemical structure of protoplanetary disks, that it's not something that can be observed with gas phase observations. So one of the revelations of very recently, from roughly 2018, is actually the detection of the first complex organic molecule, methanol, and also somewhat earlier CH3CN. But we have not been able to detect anything much more complex than that. The only more complex species is formic acid, and that so far stands at a detection towards one disk with no spatial information. For the case of methanol, after the initial detection into W Hydra, the observations have been pushing forward to try to detect it in more disks, but the current counter stands at 2 firm detections and 2 additional tentative detections. So it's not clear whether we'll be able to uncover inventory such as the one we were able to do for a young protostellar system for the case of the disk as well. So the full list of molecules detected in disk, I've tried to list here. Perhaps I'm missing 1 or 2 of the smaller ones, but the complex organic, it's really limited to these 3 guys here, and that's it. And also, as I've been stressing the need for coherent data sets, for this, we're even more so lacking these coherent chemical surveys. And this is something that is just barely starting. So the plot that you see here is one of the very first attempts to build chemical surveys of disks being carried out by Ryan Loomis. And as you see, the line richness is nothing like we're used to for the class 1 protostars, low and high mass. So I don't want you to go away from this talk and to think that protoplanetary disks are poor in complex organics altogether. The message I want you to remember is that they're poor in complex organic gases, but likely they are still very rich in complex organic ices. The problem is that all these complex organic molecules, they're frozen out and hidden in the bin plane. So likely we will not be able to observe them with facilities such as ALMA that are focused on gas phase observations. So I think for the rest of my talk, I will just briefly then try to bring this topic towards the infrared domain, because this is the FAR IR Science Interest Research Group. So I've tried to summarize essentially the different things that have been possible thus far in the infrared domain, because as you saw from the previous part, the story so far is based on ALMA submillimeter observations and essentially measurements from a very different type of instrument, from a monitoring mission to a comet. But in fact, both comets and protostars have been observed in the IR for quite some time now, and there is some work that is being done on the composition and on the volatile composition of these targets in the IR as well. So essentially at the moment, the two key workhorses for the IR studies of comets are the NIRSPEC instrument on Keck and the iShell on NASA IRTF. And so what these facilities allow us to do is to study the key dominant volatile species in a cometary coma. So this is typically your water, your methanol, C2H6, HCN, formaldehyde, methane. So the advantage of the IR domain in this regard is, for example, the ability to access a molecule such as methane, which with ALMA, with rotational lines, we are unable to probe entirely. So over here, I'm just giving you an example of some of what the data from NIRSPEC looks like. And essentially an interesting feature of an instrument such as this one for the case of comets is the ability to actually see what the molecular emission compares to to the dust position in the coma. So for example, if you zoom in on the H2CO, then you clearly see that the way that the gas is distributed in the coma is different from the dust. And this is in fact something that changes with whether the comet is pre-perihelion or post-perihelion, and is something that changes for different comets even. So our inability to consistently monitor is making the interpretation of these results more complicated. But of course, with facilities such as these, we can build up a larger sample of cometary bodies that we're able to probe. But then again, this variability, as I mentioned, for one comet, you can find that the methanol abundances, for example, enhanced, which was the case for 45P. But then for the case of Comet Lovejoy, then with iShell, it was found that the methanol here was actually underabundant. So again, when you evaluate all these results, you have to think, is this a snapshot? Is it representative? But nevertheless, these are the two very powerful facilities that are currently being in use. And so in fact, NIRSPEC is recently upgraded to NIRSPEC 2. And we had a very excellent apparition of Comet 46P Virtanen in December 2018. So there should be some new results incoming very soon on this. So I'm looking forward to seeing them myself. There are other instruments and there are domain that can also be used for similar analysis. So again, these dominant volatiles, again in the snapshot fashion. So this brings us to the SPECS instrument, also on NASA IRTF, which can be even combined with Neowise photometry. So it gives you some additional points that you can add and to see what the cometary coma look like in the IR. There's also even observations being carried out on a Canary Island telescope with the Giano instrument. But so essentially, at these wavelengths, typically you can only probe the dusty component now, and less so the volatiles such as methanol and CH4, for which you need to go to slightly larger wavelengths. So around this 1-2 micron region, you can only start to fit and model and see what the ice fraction is on the dust grains that are in your coma. And then, of course, we've had the results coming in from the Spitzer mission. So you can combine the IRAC, IRS, and MIPS data. The spectral resolution is somewhat limiting there. Then also the CRIRAS instrument on ESA VLT is very powerful for the study of comets. And again, here, this is where we're expecting a big upgrade in 2020. So first light of CRIRAS Plus should be in early 2020, I think January already. So I'm definitely looking forward to seeing some upgraded results from this as well. Then Sophia as well is giving us some very interesting results on comets. So a result from earlier this year is the measurement of the D/H ratio on comet 46P Virtanen from this good apparition that we had in December 2018. So essentially the two lines that were detected of H218O and HDO allowed us to determine the D/H in the water in the coma of this comet. And this appeared to be a very low D/H and quite different from that of 67P. So with interesting implications for where Earth's water came from. And also forecast has been used to study the dust in the coma of comets as well. And then to conclude, there was also CARI observations. In fact, there was a paper where they compiled a full sample of 18 comets that they studied, and the unique possibility from a CARI is that it was able to probe CO2 in the coma, and so we're able to determine the amount of CO2 in the water. And also there was even some work carried out with the COMEX instrument on Subaru. So essentially in the IR, what people can do is to study a lot of these dominant volatiles and try to compile a large set of cometary data and try to analyze whether it's something that's connected to pre or post perihelion position of a comet, the family of its comet, where it's a Jupiter family or Oort cloud comet, or perhaps some other characteristic like its hyperactivity, which might be a measure of the total amount of ice that's hidden in its interior. And then in the last few minutes, then I will also briefly mention what has been done for the case of star-forming regions in the IR domain. So for this, the ISAC instrument and the CRIRAS instrument have been used with the ESO VLT. So ISAC is no longer operational, and CRIRAS, as I mentioned, will be upgraded. So we should hopefully get some nicer data on this as well. But essentially, if you observe a young stellar object at infrared wavelengths, then what you typically see are the ices that you have in the envelope. So what you see in the figure here is a deep, pure CO ice absorption feature. And then actually, if you go to a more powerful instrument and consider perhaps somewhat older sources, so going to class 2 sources that may not only have the envelope but already have a disk, then you will not only see this deep absorption ice feature, but you will also start seeing emission features. So you have some hot CO emission features over here, and you even have this pure vibrational line of CO, which is likely coming from the most inner part of the protoplanetary disk. So probably the inner 1AU. And then on top of this, you also have these absorption lines. You have this full forest of vibrational CO lines in absorption. And some of these are so-called overtone vibrational transitions, therefore allowing you to actually start probing the isotopic ratio in carbon in CO, and then in turn in 13 and 12 ratio of carbon without suffering from optical thickness issues as you do typically in sub-millimeter with ALMA observations. So this is a very unique feature of this wavelength range. And yes, so then of course Spitzer and CARI both carried out observations of star-forming regions as well. And this is essentially where we were able to compile our inventory of ices that you have in the envelopes of young stars and even in the pre-stellar cores against some sort of background star. And our current count is at roughly 7 or so firmly identified ice species. So this is water, CO, CO2, methanol, methane, ammonia, and formic acid. And then some more that are less firm. So for example, OCN minus is also a suggested ice tracer. But essentially the infrared domain is our window on the ices that you have in the coldest parts of star forming regions. So this brings me to the future outlook. So hopefully very soon we have the JWST, which should help us improve our study of ices in star forming regions. Would be great to see it target the comet as well. In particular, I think 2 programs that should be highlighted in this context are the Guaranteed Time Observation Program, PI'd by Rina van Dieshoek. So this will be a protostellar survey with MIRI, and also the DDRS program of Melissa McClure, which is called Ice Age, so which will probe the ices across different stages of evolution of low mass stars. And then, of course, not only do we want to expand our knowledge of distant star forming regions, but we also want to know more about comets. And so a potential future mission that is currently being lobbied for in the frame of the latest call from ESA is a mission called Ambition. So this mission consists of a cryogenic sample return, and this would be really the next step forward for cometary science, because this would be a sample that you can study in the lab with potentially even better future techniques, and also studied in a way that we'll never be able to achieve with remote or in situ spaceborne instruments, because you would be able to see exactly what volatiles are, what the structure is of your sample, how it's ordered, how it's layered, what the exact refractory to volatile ratio is. So hopefully ESA will be funding this at some point in the future, because this would be a fantastic way forward. So then this brings me to the conclusions of this talk. So in the beginning, I was hopefully showing you and convincing you of the fact that CHO and sulfur-bearing volatiles correlate between disk materials of protostar IRS 16293b and Comet 67P, with some scatter and tentatively for the case of phosphorus and fluorine-bearing volatiles. I did tell you that the cometary relative abundance tend to be somewhat higher than the protostellar ones. We have to still figure out why that is the case and what's causing this partial chemical alteration. The main point is that solar light systems and our solar system are formed from raw prestellar ingredients that are partially modified during protostellar collapse and likely within the protoplanetary disk. And so the next big thing is, of course, deeper and higher spatial resolutions with resolution observations with ALMA, direct ice observations with the JWST, and of course, upcoming COMET missions, COMET Interceptor, and hopefully Ambition. And I'm also sincerely looking forward to surprises from the IR with the new instruments NearSpec 2 and CRIRIS Plus. So thank you all for tuning in.
Thank you very much, Maria. That was a wonderful talk. Let me put my video up here. And we will now start the question and answer period. If you have any questions, just unmute yourself and ask a question, or put it in the group chat. We'll read it out. Or anybody have anything?
I don't know if people can actually unmute themselves.
Oh, all right then.
I think we have to unmute them. So I think if there should be a button someplace that says raise hand, so people can either click that and raise their hand, or just type the question into the group chat, and then we'll unmute you and let you actually ask it. It's a little clunky, but hopefully we can get it to work.
Okay. Well, if there's no question,
Why don't we can make the last couple announcements while we give people a second to kind of think of some questions they might want to ask.
okay.
Well, I think the one thing, since we have the platform here, is to remind everybody that we have these webinars every month, roughly speaking. So usually one of the first or second Tuesday of every month at 1 p.m. we have one of these webinars. So please join us in the future.
Although in the future it's going to be a different link, so watch
It will still be through Zoom, but it will just be a different Zoom link.
Exactly.
So please join us in the future. If you have any, we can also during this time period ask any questions for us for the IR-SIG Leadership Council. You can send us an email as well, but we can use this platform also as an opportunity if you have any things you'd like to discuss with the general IR-SIG leadership. Okay. I think that's all the announcements. If you would like to give a webinar yourself or you want to nominate someone to give a webinar, you can also contact us. You can type that into the chat window or send us an email as well.
Oh, there's a question. Hold on there. Okay, David, we're trying to unmute you.
Okay, you should be on mute. No? Yes, unmuted.
Can you hear us, David?
Can you hear me?
Yes.
Oh, perfect. Thanks very much. Yeah, thanks for the wonderful talk. Really, really interesting. So yeah, I'm David from NASA Ames Research Center. And I had just a quick question, a general question about related to the ion chemistry. I don't think you really touched that, especially the positive and especially negative ion chemistry. So could you talk a little bit about that and the current state of the art, whether at 67P or you know, at 16293?
Hi, David. Thanks for the question. So for the case of the Rosetta mission, because the orbiter and the Rosina instrument was typically fairly close to the nucleus, the going argument is that no chemistry occurs in this time, because essentially it gets desorbed from the interior and essentially very quickly goes into the instrument. And so they don't expect too much chemistry to happen in this brief amount of time. So they have run some calculations to check this, and so it seems to indeed be the case. For the case of remote observations of other comets, or of course 67P at different times, then yes, there you should worry about this. So for example, CN is one of these typical radicals that is definitely a parent of coma chemistry,
Right.
also because your densities are higher. For the case of gas phase chemistry in prestellar cores, then there you do have some ion neutral chemistry going on. Typically your ions stem from the interaction of cosmic rays. So cosmic rays typically set the ionization in your prestellar core. And so any kind of ion neutral chemistry in a prestellar core is really deeply related to your cosmic ray flux. Once you get into the protostellar region, then in the hot inner zone, so once you thermally desorb near the protostar, so like inner envelope, inner hot disk, where your densities are high, there you expect it to be important as well. In the more tenuous parts of the envelope, at least for the case of complex organic molecules, the most efficient pathways are through grain surface chemistry.
Right. Okay, thanks.
Sure.
Any other questions from anybody in the audience? Okay. Well, in that case, Lisa, I think we can thank everybody for joining us today. If you do have questions, we can leave this open for another minute or so. Feel free to type something into the chat window. Otherwise, we would like to thank Maria again for such a wonderful talk, and thank all of you for joining, and please join us again in the future.
Thank you, everyone.
Thanks for having me, and feel free to reach out by email. I'm happy to answer questions.
Perfect. Thanks, Maria. That would be great. Okay.
Okay.
Should I stop the recording?
I